Okay, good morning. Welcome to the Laffont lecture. It's both a privilege and a pleasure to present Françoise Forge to you this morning. She's from the Paris Dauphin, and she will give the Laffont lecture this year. So Professor Forge is a game theorist and a microeconomic theorist. She was trained as a mathematician and has been active as a researcher since the mid-80s. Among her many accomplishments, she was elected Fellow of the Econometric Society in 1997. She's been an editor of Games in Economic Behavior since 2015. She has been one of the first to have worked on games with communication and has worked on persuasion even before the term became popular. Professor Forge, please.
Thank you. So let me, well, this seems to work, so good. Thank you very much, Zvika, for this introduction. It's a pleasure to be here and to have the opportunity to tell you about work that was realized mostly in the 60s and then afterwards. That's the idea. I don't have the time to tell you much about Jean-Jacques Laffont's work, but just very quickly, we know that the differences of information between agents were a central theme in his research, and he would be interested in this topic both when incentive compatibility conditions matter, and by incentive compatibility, here I mean truth-telling conditions. And in many of the models he handled, this was crucial. I'm thinking, for instance, of principal-agent problems with adverse selection. But there were also models where incentive compatibility conditions were not so explicit, like, for instance, rational expectations equilibria. In this talk, as I already mentioned, my goal is to show you that many ideas that are now used in cheap talk, in persuasion, were already present in some fundamental work on repeated games with incomplete information. So repeated game with incomplete information may look like a very esoteric topic, but yet there are many main ideas that have now become completely popular. And in these models as well, I will try to make the difference between incentive compatibility and cases where incentive compatibility matters and cases where it doesn't. I'm going to, as you would expect, I will tell you about game theoretic abstract models with 2 players, finitely many actions, mixed strategy. So this is really the standard game theoretic framework. I will not make any specific assumptions on the utility functions. They will not be monotonic, supermodular, whatever. They will just be von Neumann-Morgenstern utilities. By the way, because we still have in mind the wonderful talk of Stephen Morris last night, perhaps it would be better for a while that you just don't think too much about that talk, and we go back to that at the end of mine. I'm going to take models very literally. But I'm going to compare models, and so you might go back to the provocative ideas we got last night. A survey I would like to mention that is somehow a complement to the one I'm going to give today is a survey by Joël Sobel, which is still very relevant today, where he deals with parametrized models like the one he introduced with Vince Crawford. And there, of course, comparative statistics can be done in terms of the parameters of the model, and I will not have anything like that. We will, for the rest of the talk, I will have 3 parts. In the first part, I will remind you of some basic concepts for static games. Then I will turn to repeated games and show you some connections, and then at the very end I will go back to static games. So the basic model we're going to use throughout the talk is a decision problem. It's not even a game. So we start with the decision problem, which we call dp0p, because it's really the basic problem. So we put a 0, and p is a probability distribution, a belief that parameterizes the model. There is a finite set of state of nature. There is this prior belief over the set of state of nature, and there is a decision maker whom we call player 2. And in a second we'll see why he's player 2, because there is a player 1. And he has a finite set of actions. So he has to make a decision in A2, and his payoff, his von Neumann utility, depends both on the state and the action he chooses. So that's a very simple problem. There is almost no interaction. There is another player behind that, player 1, and he also has a payoff, which also depends on the state and the decision of player 2. Player 2 doesn't know the state of nature, and the role of player 1 will vary according to the model we are going to consider. Just to have a concrete situation in mind, we can think of player 2 as an employer, player 1 applying for a job, and they can do several things before player 2 makes his decision. So they can just have a conversation, an interview, that would be cheap talk. They can use intermediaries like LinkedIn, headhunters, whatever. And perhaps also the candidate can use a former employer to send recommendation letters. So the difference is that in the third case, the information that is transmitted doesn't depend on a report that player 1 would make. It doesn't even depend on his information. It really depends on the true state. So that's the difference I will make in the models we will consider. So the first case is the last one in the example. The first case is Bayesian persuasion. I believe the topic is so popular that you all know about that, but let me just remind you what it is, and also we will fix the notations for what we will consider afterwards. Bayesian persuasion in the framework I'm using is exactly the same thing as using an omniscient mediator. Omniscient, well, there is not so much to know here. What is to be known is the state of nature, that's it. In this framework, player 1 is an information designer, and what he chooses is a communication device. So that will be used throughout the talk. A communication device is just a finite set of messages. This set of messages can be a copy of the set A2 of decisions for player 2. And together with the signals, we have conditional probability distributions over signals given the state. So for every state, we have a lottery over the actions or over the signals. And the whole point of this is that given the signal he gets, because player 2 will get a signal according to this type-dependent, to this state-dependent lottery, player 2 will update his belief. That the whole point is that the analysis is done in terms of player 2's beliefs, and he can update that. And then, given his updated belief, player 2 just chooses an optimal action, because player 2 just has to make a decision, and that's it. I mean, we face a very simple decision problem. So the question is, which posterior beliefs can be reached? The answer is extremely simple, and it's just a straightforward consequence of Bayes' formula. The beliefs you can reach are all the beliefs whose expectation gives you back the prior. So that's the only condition. You can reach all the beliefs satisfying these conditions, and these are the only ones you can reach. So for instance, if you have 3 states, and you start with the prior P, you can reach P1, P2, and P3 because P is just in the convex hull of these posteriors. So now, if player 1 doesn't reveal any information in this problem, so if player 1 is completely absent, if player 1 is a dummy player, what player 2 does is to maximize his utility, his own utility at the prior, and what player 1 gets as a function of the prior is what we call UNR, NR for non-revealing, UNR of P. Now, this is what player 1 gets without using his information. Now, if he uses his information and so uses a communication device to make player 2 update his belief, then what he can get is a concavification of this mapping. So cav u, where for a function u, is just the smallest concave function above u. And that's what Kamenika and Genskov show us, that player 1 can get that and no more than that, of course. So here is a very simple example, which I borrow from Andres Salamanca. There are 2 states of nature, there are 4 actions, and here are the payoffs. I could tell you a story about these payoffs, but that would take a lot of time, so I will skip that. But you should just observe that the game is so simple that the payoffs of player 1 don't even depend on his type. So this is what other people I'm going to mention in a second would call transparent motives. And also the payoff for player 2 is increasing when, with the decision he makes when the type is 1, and it is just the reverse when the type is 2. So player 2 just optimizes as a function of the state, right? So here in orange you have what happens when no information is revealed. This is UNR. Should player 2 make the best decision for player 1, you would just have a jump here. You would not have a correspondence here. So he would take action G1, then J2, then J3, then J4, and that gives you UNR. And in red, you just have the concavification of the mapping. This is extremely easy. Once you know how it works, it's extremely easy to compute. Now, let's turn to the second possibility, mediation. So now we use the same machinery. The real difference is that now player 1 is informed of the state. And player 1 can use a mediator to reveal information to player 2. So it's the same communication device. Here I immediately use the canonical form where the action, the set of actions is a set of signals. And now, by adding the communication device to the initial decision problem, we get a mediated game. So here, player 1 is really a player. He doesn't just pick the communication device, but he's also acting by revealing his information. So here is a mediated game. There is first the choice of nature, which is of course virtual to choose the state of nature. Player 1 learns the state. He is invited to report a type. The mediator selects a recommendation to player 2 as a function of the type that was reported, and then player 2 makes his decision. Of course, the playoffs just depend on the true state and the action that is made. And at a mediated equilibrium, and this is the familiar way to proceed in mechanism design, we require that reporting his true type for player 1 and obeying the recommendation for player 2 form a Nash equilibrium. And that defines mediated equilibrium. So now here the real difference with what we saw previously is that there are incentive compatibility conditions for player 1 who must be happy to tell the truth if player 2 follows the recommendation. And we can consider the set, and we will need this set afterwards, so we can consider the set of all mediated equilibrium payoffs in the decision problem. So this is just a convex set because the incentive compatibility conditions You might ask, in this context, what player one can get as best payoff, exactly as we did in the case where the mediator was omniscience, in the case where there were no incentive compatibility conditions. And if you look at the problem, that's a bit more difficult. There is it's not clear that you could even compute that mapping. It's not clear that the concavification approach always works, as Dirk Bergman and Steve Morris have shown in a number of papers. I mean, it's not clear that this concavification approach would work in all the problems we might be interested in. And Salamanca shows that indeed you can compute this best payoff of player one under mediation, and it's a very nice construction because it uses persuasion in a fictitious problem. What Salamanca does is to transform the problem by using Meyerson's virtual utilities, and by doing so, he manages to compute the mapping by using persuasion, but in a fictitious problem, as I said. So let's see what it gives in the example. So in the example, you can compute, and you see that this mapping, the best payoff player one can obtain with mediation is, of course, above what he could get without revealing information, but below what he gets with persuasion. And it's not even linear, but still it's well behaved, and you can compute it. Now we can turn to the third possibility, which is just cheap talk. So then we just have a sender-receiver game, which we call CT1P, so cheap talk with one stage. And in that case, we have the same scenario as before with mediation, except that there is no mediator at all. So player one has to reveal or to send a message by himself. So, of course, we have, again, incentive compatibility conditions, but they are much, much stronger, because now player one cannot rely on any device. So this is just pure cheap talk. It means that if player one randomizes over signals, he has to be indifferent between the two signals he sends, because otherwise, if he were not indifferent, he would just send the signal he prefers. So here we have the extreme in terms of demanding condition. Now, it turns out that under a further assumption, the one that was satisfied in the example, we considered if player one's payoff is type independent, then the incentive constraints reduce to equalities in R. So these are just scalar equalities because there is one single payoff function for player one. And in that case, in a very recent paper, so as you saw, I mean, the Salamanca paper, the Ravid and Lipnowski paper are very recent ones. They are not even published yet. So that shows that there is still some interest in that topic. So they show that the best ex-ante payoff player one can get with cheap talk is the quasi-concavification of the mapping. So the quasi-concavification being the smallest quasi-concave function above the non-revealing function. So now we get a full picture with the four mappings. Without any revelation, then in yellow we get the quasi-concavification, which is a step function, and then the other two we saw before. So this was just to fix the notation and to indicate that by just considering these three kinds of extensions, and we could, of course, consider many other extensions of the decision problem, but just by considering these these three different extensions, we see that the incentive compatibility makes the difference because the decision maker just updates his beliefs and maximizes his payoff. So for the decision maker, it doesn't make any difference except that he has to trust the system that is used to communicate information. And what we saw is that the concavification approach in this framework always works. And we have obvious inequalities with type-dependent payoff. We have even the case of cheat talk that is very tractable, and all these inequalities can be strict when can be strict in some examples. So what is the relationship of all this with repeated games? And the question, the question comes naturally because if you take any paper on persuasion, you will see that there is a citation appearing everywhere, which is Oman-Maschler 1995. Oman-Maschler 1995 is on repeated games with incomplete information and is a typical reference in all papers on persuasion. So why and what did they do? So Sobel will tell Oman and Maschler 1995 contained the basic mathematical result in their analysis of repeated games with incomplete information. So it's 1995 and it's mathematics. Kamenika and Genskov are a bit more precise. Oman and Maschler employ formal methods very similar to ours to analyze repeated games of incomplete information. They study the value to a player of knowing which game is being played. When the other player lacks this knowledge, a fixed zero-sum game is repeated ad infinitum. Players maximize their long-run, non-discounted average payoffs, and payoffs are not observed. The fact that the informed player's initial actions have no impact on his long-run average payoffs and can thus be treated as nothing but a signal, combined with the focus on Nash equilibria, which implicitly allow for commitment, makes Oman and Maschler's problem mathematically analogous to ours. So let's have a look at what Oman and Maschler did. Oman and Maschler 1995, in fact, is a book. And this everybody realizes because the reference is clearly to a book. It gathers reports. And these reports were, in fact, written from 1966 to 1968. And they were not written by just Oman and Maschler, but there was a third man, Richard Stearns, who is a well-known computer scientist, but to the best of my knowledge, did not do much game theory since then, since the 60s. So the report were quite confidential. They did not circulate much. I was lucky enough to have a copy in the early 80s, but it's true that they did not circulate much. And they were prepared at the initiative of the US Disarmament Agency in the middle of the Cold War. This is to say that the motivation was much more conceptual than mathematical. And if you go back to these chapters of the book, you'll see that it's full of very rich examples, a number of conceptual discussions that should be perhaps read again today. The main theme was that by making use of information, as you could be tempted in the short run, you reveal that information, and this is very harmful in the long run. It's fully clear that Oman and Maschler and Stearns, for part of the book, part of the chapters, were really interested in the problem of information transmission, in the problem of long-run relationships between informed players, and they chose this model of repeated games because it was a relatively easy framework to deal with these issues because they had a fixed game to handle. So what did they do exactly? No, I'm turning to games with incomplete information. So instead of having a decision problem, now we have a genuine game. The difference is that player one also has actions. So the problem now is a very different one. At some point, we will see that the basic decision problem I had at the beginning and this game are very much connected, but for the moment, they are not. So if you like, we are starting another topic. So there is a set of state of nature. Player one is aware of that state, and we refer to it as a type. You should realize that these papers of Oman and Maschler and Stearns were written in the same way as Arsani was developing his games with incomplete information, and that's not by mistake, it's not by chance. I mean, these people were all working together, and they were interested in the same topics, and Arsani also contributed to the report I mentioned before. So both players make decisions now, they both have actions, and the payoffs depend on the actions of both players. So this is just a standard matrix game, except that we have k different games, one different matrix for every state of nature. So in fact, they were interested in the undiscounted repeated game. So the type of player one is chosen once and for all. It's a persistent type. And at every stage, the players make decisions. And they get a payoff according to the payoff function we got. They observe each other's action after every stage. Player two doesn't observe his payoff because he doesn't know the state, so he doesn't know the long-run effect of the decision he makes. The first thing they try to characterize, the first thing they focus on is the non-revealing Nash equilibrium payoffs of the game. So in that sense, it's very similar to the approach we saw in the one-shot game. We start by analyzing what happens when player one doesn't make use of his information. But here we have an infinitely repeated game. So we are, in fact, they were, in fact, trying to generalize the Folk theorem when there is uncertainty on the game that is played. And the Folk theorem, you could check that in their chapter. They knew it very well. I mean, it's called Folk theorem for good reasons. But in 1968, Oman and Maschler and Stearns were very well aware of that result. So using the main ideas of the Folk theorem, they characterize non-revealing equilibrium payoffs in the infinitely repeated game as payoffs which are feasible in non-revealing strategies and individually rational. So the first step of the research is to understand what individual rationality means in a game with incomplete information, in a repeated game with incomplete information. And for that, they analyze what player one can guarantee, and again, they first characterize what player one can guarantee himself by not revealing information. And we get a mapping, like the one we considered in Bayesian persuasion, which we call FNRP, which is what player one can guarantee by not revealing any information. Of course, it's computed in a very different way, because now player one is trying to guarantee something. It's not that player two would maximize another payoff function on his side. He sees player two as an enemy, as an opponent, because he would like to compute his individual rational level. So this mapping is computed in a very different way as the one we saw. It's just computed as a min-max, which in this case would be equal to a max-min, but it's the spirit of what player one can guarantee, so it's a min-max in the static game, in mixed strategies. So this is, you consider the expected game of player one, and you see what he can guarantee, knowing that player two could best respond in the worst way against him. And what Oman and Maschler show in '66, and this is a first report that they write without Richard Stearns, they show that in the infinitely repeated game, player one's expected individual rational level is the concavification of FNRP. There we go, same thing, concavification. We can quote Oman and Maschler, 1995, because these reports were finally published in that. Well, let's look, so it's true, there is this superficial connection. So let's look a bit more carefully and also let's try to figure out what Oman and Maschler did that can be helpful to us today. The first key of the result, and that was well understood by Kamenika and Denkov, is that there is absence of discounting, so player one can use his first actions as signals. So that's something similar between the models. The second key is what Oman and Maschler call the splitting lemma. The splitting lemma is this obvious consequence of Bayes' formula, which says that the posteriors you can reach are exactly those whose expectation is the prior. You can reach all of them, and this splitting lemma is central in all these papers on infinitely repeated games. So what the splitting lemma tells you is that player one can guarantee the concavification of FNRP in gamma infinity or infinitely repeated game without discounting. There are essential differences with what we face in Bayesian persuasion. The first thing is that here splitting is incentive compatible. It's a zero-sum game. You get it you get it for free in a sense. But here, player one is using cheap talk to defend himself. And that will have strong consequences when we go to the non-zero-sum case. And there is something much more important, is that there is no reason why here player one could not guarantee more than this concavification. And indeed, if the game were just finitely repeated, he could, in many cases, get more. So to show that player two can hold player one down to the concavification, as Oman and Maschler show, you have to work very, very hard. That's not obvious at all in this model. And one way to do it quickly is to use a result by Blackwell. So there are several proofs of the fact that player two can hold player one down to this concavification. One shortcut is to go through a result by Blackwell in 1956, and that's a wonderful paper because it's in fact about games with incomplete information, about min-max under incomplete information at a time where we don't have all this machinery, all this model of Asani. And what he does is to consider games with vector pairs. There are no beliefs there. So the idea is that if you have to punish, if you have to hold the player down to a certain level when you don't know his information, you have to consider his vector payoff. And using that, you can show that in the infinitely repeated game, player two cannot get more than the concavification. And of course, in the one-shot persuasion, you don't have to care about this. It's easy to find examples showing that indeed player one could guarantee more in a short-term game. So here you have two states of nature. We consider a zero-sum game because we are just interested in what player one can guarantee himself. Player two has three actions, player one has two actions, and you can see that action H is dominant, weakly dominant for player one in state one, while action L is weakly dominant in state two. So if the game were just played once, player one could, without any problem, play his weakly dominant strategy, and that would be very beneficial for him. So in this example, here is the non-revealing mapping, what player one can guarantee without telling anything. This is the concavification, but in the one-shot game, player one can get F1, which is above, and you can show that when there are more repetitions of the game, when the game is played several stages, you decrease gradually from F1 to the concavification of FNR, and all these mappings will be concave, and they would decrease with the number of stages of the game. So that was for individual rationality in the infinitely repeated game. So having defined individual rationality, Oman, Maschler, and Stearns characterize the non-revealing equilibrium payoffs in the infinitely repeated game. No, in their context, it might be that there is no non-revealing equilibrium. So, and also these non-revealing equilibria, when they exist, are not very interesting. So they go to equilibria with signaling. And again, it's the same technique. You starting with non-revealing equilibrium payoff, you use splitting, signaling from player one to get new equilibrium payoffs. This basic idea, you find it again as we saw in Bayesian persuasion. But here you have it with this terribly demanding incentive compatibility. So splitting, player one sends a signal to player two. How can he send a signal? Well, his first moves in the game don't matter because we have no discounting, so the first move can be used as signals. And now the whole point of having this signaling is to have player two updating his posterior beliefs over the game that is played, over the state. So the belief approach, if you read papers on cheap talk, on persuasion, you will see that there is a belief approach. The belief approach is already there. Of course, the whole point is to change player two's beliefs. And having changed these beliefs, you go for a non-revealing equilibrium of the new game. So you just have an updating. Having updated, you go to an equilibrium, non-revealing, for instance, if you just have a single stage of signaling, and you go on using the previous step of non-revealing equilibria in the infinitely repeated game. But the crucial problem is that joint plan must be incentive compatible for player one, which is very demanding. So Oman and Maschler propose another trick, another effect of undiscounted payoff, another effect of the fact that moves can be made without costing, without a too high cost, and that's what they call jointly controlled lottery. It's another tool that has been used in many other papers. There are recent and less recent applications, for instance, Matthews and Postlethwaite in auctions, Selig and Peters in mechanism design. So the whole idea is that just by coordinating their moves, players can simulate an extraneous correlation device. So nowadays, in many papers on dynamic games, you will see that it is assumed, with or without loss of generality, that players can rely on a joint correlation device. So they can coordinate on some extraneous lottery, public lottery. Here, players can do that, can internalize this. So if they both have two actions and they want to reach, and you consider two equilibria and the players want to reach the average of these two equilibria, both players will mix independently about their actions, and the trick is that they will go for the first equilibrium if the move is, if their moves are similar, let's say, if it's top left or bottom right, and they will go for the other equilibrium in the other cases. By doing so, if only one of the players randomizes this, you are sure that the final outcome has the right lottery. So this is the second tool, and what Oman and Maschler discover through examples, Oman, Maschler, and Stearns discover through examples, is that if you have signaling, then jointly controlled lottery, and then another stage of signaling, you get more equilibria. So they find two ways of getting new equilibrium payoff, signaling and compromising, and they show that there is no reason why that will stop. And indeed, in 1985, Sergio Hart provides a full characterization of Nash equilibrium payoffs in the infinitely repeated game, and he shows that you can alternate signaling and compromising ad infinitum. So let's just look at the statement. So the statement is that a payoff is a Nash equilibrium payoff in the infinitely repeated game if there is a die martingale. It's a special martingale, I'll tell you more in a second, which would start at the point and would converge to a non-revealing equilibrium payoff. So what you do, you look at the correspondence. So the convergence is to posterior and the payoff, and you require that the payoff is a non-revealing equilibrium payoff at the posterior you reach. So this is to show that the belief approach is used throughout the process. The first thing you find in this result, and that's why I'm showing it to you, is the splitting, and the splitting just makes the process to be a martingale. You find it the old property, the standard property that believes posteriors just update to the prior, and this is true at every stage, it generates a martingale. No, these martingales are not any martingales, they are die-martingale. What does that mean? That means that there is incentive compatibility, and that means that every time the posterior changes, the payoff of player one has to remain constant. So that's the strong condition that expresses the incentive compatibility conditions for player one. So you cannot just consider the martingale, which is a rather trivial property in this framework of signaling. No, you have to have a further condition which is extremely demanding, which is the incentive compatibility. And the die-martingale accounts for this incentive compatibility. And it's not artificial. You can find examples where indeed you need this long process. There are Nash equilibrium payoffs that require such a long process. And the topic is still alive. I mean, quite recently, there were attempts to extend this result to discounted games. So this is just to indicate that there is still research going on the topic. Of course, this looks like quite esoteric to have such a complicated, repeated game with a die-martingale. I agree that looks like a very, very narrow topic. Let's gradually move to the connection of all this with the static decision problem we started with. So let's make a further assumption. Let's assume that in the infinitely repeated game, the moves of player one only serve as signal. He can choose actions, but they have no impact on the payoffs. So let's do that. If we do that, then we in the one-shot game, we are back to the decision problem we started with. Because in the one-shot game, player one has an action that doesn't have any impact on the payoffs. But in the infinitely repeated game, player one can send signals. So with this assumption, the two problems start to look similar. And let's make another step. Let's consider correlated equilibria in the infinitely repeated game instead of Nash equilibria. By correlated equilibrium here, I mean the most straightforward interpretation of Oman 1994. So I just mean that the players can observe correlated signals, any kind of signals that are correlated for player one and player two, but do not depend at all on the game, on the state, or anything else. It's just that there are sunspots, player one and player two can observe, but they need not to make exactly the same observation. So it's not necessarily a joint signal. I mean, there can be some correlation, but they may have private correlated signal. The whole point is that player one observes the same signal, whatever its type, which may be relevant, for instance, if there are privacy concerns. Now, what I did, and it's a very, very, very old result, I'm sorry, but to bother you with something that is so old, but still, I think we can have another look at it in the light of what was done since then on games with communication. So now, suppose we consider the superset of Nash equilibrium payoffs, which are these correlated equilibrium. So very, very little change. We just assume that the players can observe these correlated signals that have nothing to do with the game. Now, if we start with such a game of pure information transmission, so player one's moves are just costless, they are just there to signal, then the correlated equilibrium payoff of the infinitely repeated game are just the same thing as the mediated equilibrium payoffs of the decision problem we started with. That's the characterization of correlated equilibrium payoffs in the infinitely repeated game. So this is a connection, a very straight connection, very precise connection between the infinitely repeated game and the one-shot mediated game. So that means that as soon as you have these correlated signals, you don't need dimartingales, you don't need long process. Everything you need to consider is the one-shot game, but with mediation. And even if the game is of pure information transmission, you may need to have the dimartingale for Nash equilibria. It's not that the game is so simple that information transmission is simple. No, for Nash equilibrium, it's still very complicated. No, this formulation is still it shows the connection between infinity repeated games and one-shot game, but still it's not very useful for application because you still have this infinitely repeated game here. But you can, if you look more carefully at the proof, there is a lemma that I'm not sure it was ever stated in this way, but I think it's quoted in this way. But the main tool to prove this result on infinitely repeated game can be entirely formulated on one-shot games. If you take every mediated equilibrium payoff of the decision problem we started with, so this was the intermediate concept we saw, you can achieve it as a correlated equilibrium of the one-shot game, of the game with the one-shot stage of cheap talk. So remember, the beginning we saw 3 games: Bayesian persuasion, mediated equilibrium in the decision problem, and the third game was the cheap talk game. So here you have a connection between the mediated equilibria of the decision problem and the correlated equilibria of the cheap talk game. So that's another connection. So these games, as we saw, give the mediated game and the cheap talk game, in principle, are very different. So you expect very different payoffs. Yet, if there is this little correlation at the beginning, you get exactly the same set. And this result was, in fact, a similar result was, in fact, established by Bloom in 2012. He showed the same result for the best mediated equilibrium payoff in Krobost and Sobel's uniform quadratic case. So this best mediated equilibrium was demonstrated, was characterized by Goldsman, Horner, Swintani, and Pavlov. So what they did was to consider mediation in the basic example from Crawford and Sobel, and then what Bloom showed is that for that equilibrium you had something analog. You can get this best mediated equilibrium by just having a correlation in the cheap talk game. And of course, in that context, best mediated equilibrium makes sense, because as soon as in the basic example from Crawford and Sobel, as you remember, as soon as player 2 is in equilibrium, the equilibrium payoffs of the players become aligned. That means that there is a sense to talk about best equilibrium, because player 1 and player 2's payoffs just differ by a constant. Of course, in these models, there is no reason why you could have the same preferences for player 1 and player 2 over the equilibria. So this is one of the first results, once you formulate it in this way, that can be interpreted as implementing a mediator by cheap talk. Here, of course, the implementation still requires correlated equilibrium, but if you have more than 2 players, you can obtain similar results for Nash equilibria. So the way this kind of result was used was more in replacing the mediator by cheap talk, because here you have a relationship between mediation and cheap talk, was more developed in that direction, and then these were one-shot games with communication and possibly with many players. I definitely don't have the time to go through that, so let's see what we have done at this point, we have seen what happens when we have the decision problem in a single stage of cheap talk. That was the game CT1P. We have also considered the infinitely repeated game. We saw a number of connections. So last topic that I think was completely generated by this analysis of infinitely repeated games is the games with long cheap talk. So let's turn to this. So now we consider a fourth extension of the decision problem, which is long cheap talk. So again, there is a single choice of player one's type, of state, player one learns the state, and now the players can talk for as long as they want. So here it's a one-shot game. Player two just has to make a single decision. We are back to our decision problem, but now the players can talk before player two makes his decision, and they can talk as long as they want. Now, this talk is not polite in the sense that we allow player one and player two to talk simultaneously. There was a paper by, that was never published, by Oman and Art in the 90s, where they had this title, Polite Talk is Not Cheap. So they started by analyzing polite talk, but then they went to the more general possibility of having the players talking simultaneously. In the context we saw before, this doesn't make any difference, of course. If we have this equivalence, the set of mediated equilibrium payoffs is so efficient. I mean, is so large, allows for so many possibilities. As soon as we know that it's equal to what the players can do with a single stage of cheap talk, it's a consequence of what we saw before. It's also equal to what they get with infinitely many stages of possibly infinitely many stages of cheap talk. So if we allow for these correlated signals, long cheap talk doesn't matter. But for Nash equilibrium, it does. So from that point on, I mean, in the early 90s, this topic became extremely popular, or at least, I mean, people started to be interested in the long cheap talk. But for Nash equilibrium, because then it really matters. So you'll find a number of papers showing that long, and it doesn't have to be very long. I mean, it can be, sometimes in some of these papers it's not that long, but the fact that you repeat the cheap talk can matter. First of all, there was an example by myself, that was just, in a sense, a rewriting of what, and that's why infinitely repeated games really matter. That was a rewriting of what was already known in the mid-80s, but just to demonstrate the role of the communication, the detailed way in which the players would talk to each other, and why long, and in that case it was very long cheap talk, would matter in Nash equilibrium. But of course, even in that case, mediated equilibrium does even better. But still, you can show that there are Nash equilibrium payoffs that cannot be achieved unless an unbounded number of cheap talk of cheap talk stages is allowed. And then there was this paper I mentioned about polite talk, and Sergio Ward and Bob Oman felt they had to go back to this characterization that was found in infinitely repeated game and go to long cheap talk. And so conceptually it was quite, I think it was quite obvious that long cheap talk, as it was characterized by Sergio Ward, would translate into models with the single stage of decision, but finally the writing, the technical writing of that paper was far from obvious. And so this gave rise to a paper that I believe is very well known, the long cheap talk paper by Oman and Art. And they use these die martingales. So the tool that was previously developed for infinitely repeated game, and then that goes back to Oman, Maschler, and Stearns, which had well understood that there was this, that you need to alternate signaling and compromise. They finally came out with that paper, which is a very interesting paper, and of course was crucial in other research papers. And then people started to ask whether in Crawford and Sobel model several stages of chip talk could matter. And Krishna and Morgan indeed found very nice examples where in the model of Crawford and Sobel, just the uniform quadratic example, two stages of chip talk could improve, Pareto improve the payoffs, the equilibrium payoffs of the players. And in that case, from that time on, long chip talk became more popular. And there is an unpublished paper, I think the authors are still working on it, so Chen, Goldsman, Horner, and Pavlov are now studying long chip talk in the Crawford and Sobel model. They consider straight talk, which means that it's a take it or leave it at every stage. So either you say something or you stop the game. So you cannot use chip talk to decide on different ways of talking afterwards. You just either you talk or you stop. And they show that there are equilibria, new equilibrium payoffs you can generate in this way, of course for some values of the bias in the model. Coming back to Ravit and Lipnowski, the paper on we saw at the beginning for chip talk, one stage of chip talk in the case where player one's payoff is type independent. So remember, they could characterize the best payoff player one can get by chip talk with a single stage of chip talk as the quasi-concavification. When they started to present that paper, it seems that they didn't know about the long chip talk business. And of course, an obvious question was, what happens if player one can use several stages of chip talk? Can't he get more than this quasi-concavification? And the answer is no. In their model, long chip talk does not matter for player one. Player one cannot do better with several stages of chip talk. It's not true for player two. They have a simple example where with a further stage of chip talk, player two can do better. But yet, the quasi-concavification they get is robust to adding stages of chip talk for player one and player two. Well, that's what I wanted to tell you about these connections, superficial connection, a bit deeper connection between repeated games and games of information transmission and persuasion games. Of course, the models I presented are extremely narrow. It's a very specific model, just a decision problem. So, of course, we should look at more general problems, and there are already many papers dealing with more general models. Just to conclude, I would like to mention some possible works that build again on the work by Oman and Maschler. So we talked about the first chapter and also the last chapter in Oman and Maschler 1995, but there is, of course, there are intermediate chapters, and one thing they do is to consider games with lack of information on both sides. So in that case, you have the same kind of infinitely repeated game, but both player one and player two have private information, and in the simplest case, they just have independent, there are two states, play one, observe one state, play two, observe another, and you just have beliefs over the two states, and the payoffs would depend on these two states. And what Oman and Maschler do is to characterize the min-max and the max-min. They consider zero-sum games. They characterize the min-max and the max-min, and they show that these need not to be equal in the infinitely repeated game. And this model has given rise to some papers. First, it's used to characterize correlated equilibria in more general models. This is just to make the connection with what I said before. More interestingly, there is a whole literature on splitting games. These are stochastic games where the variables chosen by the players are just the beliefs. So these are zero-sum games, but they are really using deeply the fact that beliefs can be the variable, and they study the value of these games, which are kind of cousins. They are very related to these, but they have much nicer properties. There are extensions of the result of art and of Oman and art for the case of lack of information on both sides, and it's a pity because these papers were never polished or published, so they are still working papers from the Center for the Study of Rationality in Jerusalem, and I think there are many wonderful ideas to be used from these papers also to make connections with cheap talk in games with lack of information on both sides. Something that is maybe relevant is that these papers were written as a thesis in 1990, and they already used the long cheap talk of Oman and art, which came out in the way we know it in 2003. Even more related to what we are discussing these days, there is a very recent study, very recent working, maybe not working paper, at least presented at conferences by Kessler, Laclos, Tomala, and Renaud. So they use persuasion of a single, they model persuasion of a single decision maker by two competing designers. And these designers have control of a different component of information. They both, for instance, would like to convince of the quality of their own good, and they are competing. And so these authors make a direct use of the theory of Oman and Maschler. So they will, instead of just concavifying, they will convexify and concavify. So they will find values for what happens for short-term or long-term persuasion. So that's really using these results in a completely different context. So in their case, they really make a full use of what was realized by Oman and Maschler. More general models, yes, the only thing I can recommend is that you read the survey by Dirk Bergman and Steve Morris. That would be a way also to make a connection between what Stephen told us yesterday and the very simple models I mentioned today. What they would explain, what they explain in these surveys is that the concavification approach is of course very limited. You shouldn't expect to use it, and that there is no reason why you would like to use it in general. But there are two-step approaches that you can indeed use, and combining some of the ideas I tried to convey today, and the ideas that Steve developed yesterday, you can indeed use a two-step approach to persuasion or communication. Brief summary. So the only thing I try to do is to show you that you can get a variety of solutions, a variety of solution concepts, variety of models, and the slightest difference you introduce makes a difference in the solution you get. That was these different mappings we got at the beginning. So that there is a multiplicity of ways to model communication, and if you take it literally, it gives you very different solutions. And also, I refer to Nash equilibrium and correlated equilibrium. There are many other solution concepts you can use, and this adds to the variety of answers you can get. So we should rather be careful when we have a model, because we get a very different answer depending on all these variants we think about. So I think even if we stick to this literal interpretation, it's very important to know, to characterize what we get. But also, in some cases, as I tried to show you, just a little change would make these solutions equivalent to each other. And I think that's also another clue that if you, for instance, have these little correlated signals that have nothing to do with the game itself, that can make solutions equivalent. So we start by assessing the difference between the different approaches, but then with a little difference, a little new ingredient, we can make, in fact, these solutions equivalent. That may even strengthen our questions on the right model to use, for instance.
Okay, thank you. We have time for a few questions.
I have a comment, which is that I believe that Hassani credited. Can't hear you. Hello? Yes. Okay. I believe that Hassani credited Aumann and Maschler for the term type, actually. So when
thank you.
When he first went around, so Aumann has. So I've asked Aumann about this, and consistent with what you said, they were having lots of conferences, and Hassani's ideas were floating around, and yeah, he wasn't using that term before, and they suggested it apparently.
Thank you. That's a good, it's a good compliment to. Yeah, thanks.
Any other questions or comments? Okay, so in that case, thank you again.